I was watching a code dumped video by George where he explained that the compiler is a toolchain which performs multiple steps like preprocessor, creating assembly, creating object files, and linking them. That was interesting for me because I took the preprocessor and creating assembly steps for granted. I think most of us probably have, because we've usually passed in the -o flag with the object files and then we link them together, and that's usually what you learn in a computer architecture course. But obviously I knew that C and C++ code could be created into assembly. I just never realized how to do that in a compiler step. So that's kind of what I wanted to look into in this video. The following steps are pretty much the intermediary steps that the Clang compiler does. We can create a main executable by doing clang ++-o main.cpp and passing in any other files that might be useful, like add.cpp in the example that we'll go over shortly. But the point here is when we run this command, Clang actually does all these things underneath the hood. And I just wanted to kind of go through them and see what the output of each one is. The first thing it does is it takes the main.cpp file and it runs through the preprocessor, which does things like expanding macros and headers. That is going to create the main.ii file. Now then there's a step called LLVM bitcode. Now this step turns out generates some sort of bitcode that can be used for things like optimization. After that, it goes to creating the actual assembly code, and then the assembler will turn this .s assembly file into an object file. And these object files are things that we're all familiar with. These object files get linked and of course eventually create the main executable. The compiler actually really is a toolchain that does a lot of things behind the scenes. It does the pre-processing step to create the main.ii file, which kind of expands the C++ code. It might do this bitcode step, then it will create the assembly code, which will get converted into an object file, which will finally get linked. So if you're ever wondering why a compiler is taking so long, maybe this is the reason why. Let's look into these steps more carefully. The first question is, how can we generate the results of these intermediary steps individually? There is a way to do this for each step. So if you want to generate the main.ii file, you can pass in the -E flag, and that will kind of just run the preprocessor and create this .ii file. And of course, there are similar commands for generating the bitcode, as well as the assembly, which is the -S flag, as well as the object files, which this is something that we might already be familiar with. And finally, the step to convert those object files into an executable. Then the next question is, how can we do this all at once, right? So thankfully, Clang has a nice little flag here called -save temps, which is what we're going to be using to get all of these files. I've created a simple main.cpp file here. It's got an include with add.h. Add.h contains the function header for the add function, which takes in 2 integers and returns an integer. Inside here, we're including that so that we can call the function. The add function is defined inside the add.cpp file. And of course, this just adds 2 numbers. Now I'm going to go to the makefile here, clang ++-save temps -o main, and then main.cpp add.cpp. So let's run this command. So I'm going to do make in this directory, and it's going to start creating all these files. So let's go back here and iterate through these files one by one. So what does the preprocessor do? So it's expanding the includes. So in here, it does a bunch of random stuff, but the important thing here is that this include file, which has add.h, is getting included inside of the main.ii file. This was very interesting for me to actually see this step. Now let's see what happens if we say, do a subtract. Now if I save that, and now let's run make clean to clean the files. So I'm going to do make once more. And now let's go to the main.ii file here And now you can see that add and subtract are now inside of main.ii file. So again, this is what the preprocessor does. It expands macros and includes the headers. So the next step here is the main.bc file, which is going to create machine code. So if I go here, well, yeah, it looks like machine code. It's not really readable, so let's not really go through that one. Let's go to the assembly. So the assembly is in the main.s file. Funnily enough, I've actually used assembly in college in my computer architecture course. If I wanted to guess at what it was doing here, I would say, well, it's moving something. And looks like here it's calling some add.ii function. Now add.ii, that does sound familiar. We know that in the main.cpp file, we are calling the add function. And inside of the assembly, we can see a call to __ capital Z3 add.ii. So when I look for this, I should see it right here. As you can see, it is defined in the add.s assembly file. Isn't that very interesting? And now that we've understood where the assembly code is, we can finally check out the .o file, which again is something that most of us are already familiar with. It's basically machine code, so we can't really understand any of it, except it is interesting here that that same __ Z3 add.ii variable or function or whatever is here, as well as main. But anyway, this explains to us what happens underneath the hood. Obviously right now this is a very simple example, but what happens when you include IOStream? See out this variable. Actually, let me do that, and let me do... See, let me include IOStream, and finally, let's see how large the file gets if we do a make. So if I do this make file here, this is where it gets interesting. Let's go back to looking at these steps. Here we've got main and the preprocessor. How large do you think the preprocessor step is going to be, as well as the other following steps, now that we've included IOStream and we're doing stdc out? I'm going to go to main, and there you go. This file has now ballooned up to 50,000 lines of code just because I included IOStream. I think this is where one of the problems happens with C++ is when you include a bunch of things like from the standard library, the preprocessor step gets really large. And now if we go to the main.s file, again, the assembly code, really large, but it's being generated because we included the IOStream. Now, thankfully, it looks like the main.o file is not that large. It looks like it's only about 100 lines of code. And I think that's what kind of the interesting thing here is. If you're including a large library, it's going to really increase the preprocessor step and also increase compile times, which I know is a common problem that many engineers and engineering teams face. And then they're like, well, why would we want to include the standard library if it's going to slow down our compile times by a couple seconds here or there? This was a very interesting video for me because I learned a lot about all of these steps. Also, it was very interesting to see that you can, one, create all of these steps individually, as well as create them all in one command. Hopefully, you've learned a thing or two about what happens in the intermediary steps when you run the compiler, what each of these steps outputs are, and how the outputs can change when you include small files or when you include a large standard library file. Thanks for watching, and I'll catch you guys next time.